exciting.
Alright, so here we go with the flying pig. Now, no doubt this is what you've all been waiting for all year. This is the reason you took grade 12 physics, just so you can see the flying pig. No, he does not fly around the room. I didn't tell you that. Well, maybe I did.
You did.
Alright, so I'm reading from the sheet here. Discussion. When an object travels at constant speed along a circular path, we say that it has uniform circular motion. If its speed were changing, then its motion would not be uniform. Any object moving in a uniform circular motion is accelerated toward the center of its circular path. This acceleration is called centripetal acceleration and equals v squared over r.
Okay, wait a minute. Can I ask a question?
Sure.
Centripetal.
Centripetal.
I know, but the other one is when you're inside of it.
It only exists
Yeah.
when you're inside it, right?
Okay.
Since the net force on any object equals ma, during uniform circular motion, the net force called centripetal force equals mv squared over r and is directed towards the center. This is what happens when an object suspended by a string moves in a circular path, which is called a conical pendulum. So what the pig is going to do, he's actually going to fly in a circle. Which way is the tension though? Well, it's up at an angle, okay? So we got lots going on here. We've got tension, we've got equilibrium in the vertical sense, we've got circular motion, we've got components, lots going on. The string of a conical pendulum sweeps out a right circular cone. In this experiment, you will measure the height of an object, the speed of an object that is comprising a conical pendulum and show that the net force is mv squared over r. So, pre-lab analysis. Draw the net force vectors, a free body diagram, that act on a conical pendulum. Ignoring air resistance, note that there are only two forces that act on the pendulum bob. In this case, the pig. His name is Bob. Bob the pig.
Oh.
One is mg, the force due to gravity, and the other is string tension. So step number 2, with dashed lines, show the horizontal and vertical components of T. Also label the angle theta between the tension T and the vertical. So let's do that first, under step number 2. Okay, so you got it like this. T. Here's Bob the pig. Yeah, it's right on the page there. Right at the bottom, right? And you've got a sort of a circular path. We are to draw the horizontal and vertical components of T. I'll do them in red. So you draw these ones. We've got this one here, and we've got this one here. We're going to call this one TY, or tie. We're going to call this one...
That was like a 1 on the Bennett scale.
Yeah, it was pretty cool. We're going to call this one TX. Tex.
No.
No?
That one's not as
Pi and Tex?
I don't even know if you're... That wasn't even a 1.
That doesn't even count, right? Yeah. And our theta is right in there. Okay. Step number 3, flip the page. Does the pig accelerate in the vertical direction? I guess you really got to see the pig fly first, don't you?
Yeah, dude.
Let's do that. Okay. Let's get the pig fired up here. Kind of fun, isn't it?
Will it ever stop?
It doesn't actually stop. We've actually done experiments. Once I give it a little push, it seems to always go to the same angle, the same speed. Everything about it is the same from year to year.
What if the batteries die?
Now, if I turn the wings off, because people have asked me this, what happens when the wings are off? If I give them a push, did you notice before that I see he's facing forward here, but is he going in a circle?
That's a weird shape.
No, it's sort of a weird shape,
Turn
And
the
it
wings
looks like
back
it's slowing
on.
down.
and he's actually slowing down.
Turn the wings off, we gotta get
the
them going.
wings actually do something. Like, I thought it was just for fun, you know? But the wings actually perform a function in this case.
Get him going again.
Yeah, I guess, I think it's just moving the air, cutting down on the air resistance or something. I'm not really sure what's going on, but the wings actually do perform a function. All I have to do is just sort of give them a little, oh, out the bad push.
Gotta get going.
And there he goes. Okay, so the question is, and I always do this, I always put my sheet down and then lose it. There we go. So, question number 3, step 3 says, does the pig accelerate in the vertical direction? Does he accelerate vertically? No, he does not. What does this tell you about the magnitude of the vertical component of T and mg? I'm just going to turn them off so he's not killing batteries and making noise. What does this tell us then? So the answer to step number 3 is no, he doesn't accelerate vertically. What does it tell you about Ty? Ty is equal to mg. Very good. The weight of the pig is equal to Ty. Step number 4. Does the pig accelerate in the horizontal or radial direction? Does he accelerate horizontally? Speed doesn't, but the direction certainly does, obviously, right? So knowing that the net force in the radial direction for an object in uniform circular motion is the centripetal force, what does this tell you about the magnitude of the horizontal component, Tx, and mv squared over r? They are also equal, right? So in other words, Tx is equal to mv squared over r. mv squared over r. Alright, step number 5. Write an equation that shows how the horizontal and vertical components of T are related to the weight and the centripetal force. And they've given you a hint. They've written tan theta is equal to opposite over adjacent. Opposite is Tx, adjacent is Ty. In other words, substitute these two things in for Tx and Ty. That's under step number 5. So I'm going to have Tx's mv squared over r, and that's all over Ty, which is equal to mg. And what do we get out of that? Guess what happens? Yeah, once again, mass always seems to cancel out. Mass always seems to cancel out. And so I get tan theta is equal to v squared over r over g. Can I write this over r over g?
No.
Like I'm dividing by r, then dividing by g. Can I just go like that?
Yeah.
Right? So the tan of the angle is equal to v squared over rg. Step number 6, algebraically solve for the tangential speed of the pendulum from your equation. Step 5, in other words, isolate v. Isolate v here. So rg comes up here, right?
Square root of
V squared is equal to rg tan theta, or v equals square root of rg tan theta. The speed of the pig, Bob, is the square root of the radius times g times tan theta. Now what we're going to do is we're going to actually calculate the speed, like measure the speed, I mean, and see if this is actually true. We just derived this, we're going to actually see if it's true. Quinn, you can put pause now.